Okay, let's talk about catalysts. Catalysis, it refers to catalysts, which are substances that speed up a reaction without being consumed in the reaction themselves. All right, and so we can easily diagram this, represent it in a reaction coordinate diagram, which you've seen. We've got our reactant energy right here, our product energy right here. You have features like the delta H, the change in enthalpy, which is just going to be products minus reactants. And we have the activation energy. Now, if you have an uncatalyzed reaction, your activation energy is from the reactant energy all the way up to the transition state. So here's our transition state. And this is the activation energy. Now, you might remember that, especially when we talked through the Arrhenius equation, that the higher the activation energy, because it's endothermic, the greater that activation energy is, the slower the reaction. Okay, so anything you can do to lower that activation energy may not change any of the other features of the reaction, but it catalyzes it. That is, speed up the reaction by providing a different pathway. And that's essentially what a catalyst does. So if you remember back to my description of going from Denver to Dallas, I got on my motorcycle and I rode all the way up to the top of the mountain. And then it was pretty much downhill all the way to Dallas, okay? And that's the way that worked. But first, I had to overcome that energy barrier by taking this path over the mountain. Well, a catalyst provides you with a different path, and that different path has a different or lower activation energy. And because the activation energy is lower, the reaction goes faster. So that's what a catalyst does. It provides you with a different pathway. So different pathway that is faster because it has a lower activation energy. So catalyzed pathways, activation energy. Don't laugh at my spelling or my handwriting. Shame on you. Okay, so a catalyzed pathway is different than the uncatalyzed pathway, and that catalyzed pathway has a lower activation energy. And so both of these would represent the part of the catalyzed pathway. And with the Dallas to Denver trip, it's like having a tunnel through the mountain. I just go through the tunnel. That's a different pathway, which requires less energy to get to it than having to go all the way to the top of the hill. All right? So let's sum up. A catalyst is a substance that speeds up a reaction without being consumed itself. It lowers the activation energy of the reaction by providing an alternative pathway. That alternative pathway is a different mechanism. It's a different reaction mechanism because now you've introduced the catalyst, which facilitates the reaction by lowering the activation energy. It doesn't affect the delta H. You can see down here that your delta H is unaffected because it's down here well below what's going on in the catalysis portion. Here's the catalysis portion of the reaction, and that does not affect the difference between the product energy and the reactant energy. So the delta H, that stays the same. Catalysts can be homogeneous or they can be heterogeneous. If they're homogeneous, they're generally in the same state. A heterogeneous catalyst, the most famous example for most people, is a catalytic converter on their car. And catalytic converters, they have a ceramic honeycomb inside a metal shell, and embedded in that honeycomb are little metallic dust particles, either palladium. I think they used to use platinum. It's got to be terribly expensive. And catalytic converters are expensive. And what happens is, as these gases, the unburnt hydrocarbons, where you haven't had complete combustion in your engine, are going through the catalytic converter, they attach to this palladium metal. I think typically that's probably going to be one of the primary metals, and that facilitates the burning of those unburnt hydrocarbons. Catalytic converters operate at tremendously high temperatures. Okay, so those are the basics. So there's one more thing I want to talk to you about with respect to both catalyzed and uncatalyzed reactions and reaction coordinate diagrams. It's possible to represent the mechanism for the reaction, or at least some semblance of the mechanism. With respect to this catalyzed two-step mechanism, we would say this is the first elementary step, this is the second elementary step, and right here, what do you think this is? Well, since it's a two-step reaction, this is going to be an intermediate. That's what we're representing here. Now, here is the activation energy for the first step, and I'm just going to extend the reactant energy over here. Here is the activation energy for the second step in this catalyzed reaction. Which step, the first step or the second step in this reaction coordinate diagram, do you think is depicted as the slow step, the rate determining step? Well, if you guessed step 2, you would be correct, because the activation energy for step 2 is higher than the activation energy for step 1. And so this is going to be the slow step, which we call the rate determining step. And this is our fast step. Okay? These are the two transition states in the catalyzed reaction. So this is a little bit crude, but and I had to go ahead and draw it because I'm having a little bit of problem with my software. But in any case, here we go. Here is an uncatalyzed reaction. Here's my reactant energy right here. Here is my product energy up here. First thing I want you to notice is that the product energy is higher than the reactant energy. That means my delta H is going to be positive, because overall I'm going to have to put energy into this system. So I'll have a positive delta H, which means that this is an endothermic process. I just want you to be able to recognize what an endothermic reaction progress diagram looks like. This is clearly an exothermic diagram down here. You have product energy lower than the reactant energy. You'll have a negative delta H. Here you're going to have a positive delta H because your product energy is higher than your reactant energy. It's also a two-step mechanism. Now, this is not a catalyzed reaction. You can have multi-step reaction mechanisms depicted in uncatalyzed and catalyzed reaction progress diagrams. This one happens to be uncatalyzed. And it looks pretty much the same, except you don't have a transition state up here. So at any rate, the first step has the highest activation energy. So this is going to be your slow step. You do have an intermediate down here, and then you have a fast step here. Okay? So I just wanted to throw that out there, make sure you could recognize it. All right, so here is a clicker question. We're going to identify a couple of items in this clicker question. So a catalytic mechanism proposed for the depletion of ozone by chlorofluorocarbons in the stratosphere is. Years ago, when the world was putting out tons of refrigerants A lot of the gases, which were the chlorofluorocarbons, migrated up into the ozone, which is ozone is O3. That is ozone right there. And up in the stratosphere, it protects us from UV radiation. Down here in the troposphere, where we live, it's actually toxic. But in any case, you can look that up. But what was happening with these chlorofluorocarbons is you were getting these chlorine radicals. That is, you were getting chlorines that had an unpaired electron. Now, this chlorine radical with this unpaired electron is a very reactive species, and it was reacting with the ozone and producing another radical. It was producing a radical chloroxide molecule and an oxygen molecule. And this chlorine or chlorine monoxide radical would go on and would destroy another ozone molecule, regenerating another radical chlorine, and the process would just go on and on and on, and it was creating big holes in the ozone layer. So lots of UV radiation was hitting the Earth, and cancer rates went up. And ultimately, that is just not good for Mother Earth. Okay, and so international bans were put on the manufacture and the use of these chemicals, which has, I'm hoping, helped. And you don't hear much about it anymore. So presumably the situation is better than it used to be. So at any rate, let's look at this reaction mechanism. Now, the chlorine radical is actually the catalyst that speeds up the destruction of the ozone layer. Normally, you'll have two ozone molecules which will ordinarily be split. UV radiation comes in, it splits it up into three O2 molecules, and this is fine. That is the purpose of ozone in the stratosphere from our perspective. That's the good that it does. But if you have these chlorine radicals, which are catalyzing the destruction of the ozone before the UV radiation strikes those ozone molecules, you don't have those ozone molecules anymore to save you from the impact of high UV radiation. So in this case, the chlorine radical is the catalyst. And you can see that because it's introduced, and this would be a homogeneous catalyst, it's introduced to the reaction in the first step, and in a subsequent step, it gets spit back out to do its business again. So you can always tell a catalyst because you can cancel it because it's not part of the overall reaction. It's a catalyst. It speeds up the reaction without being consumed in it. That means that it's either a stationary catalyst or it simply gets spit back out as a product in a subsequent reaction. Now, we also have this chlorine monoxide radical, which is an intermediate in this reaction. And so that winds up giving us ozone plus ozone. And so here's our ozone, and we've got two of them. And that takes us to one oxygen plus two oxygens is three O2s. And we have our balanced reaction. So which statements about this mechanism is true? O2 is a reactant. Well, that doesn't seem true. Chlorine monoxide is an intermediate. I think we've solved that problem. Ozone is decomposed to O2, and O, well, I'm not really seeing a whole lot of O up there. And chlorine radical is the catalyst. So I'll leave it to you to figure that out. Okay. And last thing, here's our chlorofluorocarbon, like Freon. This is Freon. And here is the Freon, which decomposes to the this molecule and the chlorine radical. and that goes on to catalyze the destruction of ozone in the stratosphere. Okay? All right. There is our catalyst. Chlorine is used to initiate the reaction and is regenerated in the last step. And that, ladies and gentlemen, is the end of chapter 14. Hope it wasn't too painful.